Imagine you're planning a trip. Say you want to get from La Jolla to Cathedral City. How do you plan this? You certainly don't plan every stop sign on the way. Rather, you might abstract the problem. You know how to get from La Jolla to Temecula, and you know how to get from there to Cathedral City. In other words, when planning, we often abstract the problem to break it into smaller parts that we can find a solution to more easily. Reinforcement learning gives us a formulation of planning as search over a graph. Here, nodes are states, us being in a particular place, and edges are different actions that we can take in a given state that get us to a new one. Here that's driving in one direction or another. The classical view of planning then is searching across this graph from the start to a desired goal, and this then gives us a series of actions that allows us to achieve our goal. Intermediate states, here Temecula, make planning easier by reducing the size of the graph that needs to be searched. However, there is a cost associated with choosing subgoals as well. So, how do we choose subgoals, and how do we balance searching for actions and expending this upfront effort to make action search easier? Here's one observation. Maps aren't just a collection of nodes in a graph, though this is what your GPS uses to plan. They're physical objects, and here are some things that humans do with maps while planning. People fold maps, or more likely today, zoom in, or they use their hands to bound a part of the map. All of these operations select the region of the map to focus on now. How might such actions, bounding of a region of space to select what to focus on next, guide planning behavior? To study how such a strategy might guide planning behavior, we formalize this notion in a computational model. To do this, we first needed a domain that requires planning, is familiar enough to people that they know the effects of their actions, spatial, and that allows for the interleaving of acting and planning. We chose the block tower construction task. Here, the task is to recreate the outline of a tower in a building area from a selection of blocks. Blocks can only be placed on top of other blocks, and once a block has been placed, it cannot be removed. There are 16 structures used in the upcoming experiment. These structures were hand-designed to present a variety of difficult planning problems. Let's look at a toy example. On the bottom, you see all possible placements. In green, you see goal states, and red, you see dead ends, and since you cannot take blocks away, you need to make sure to not end in a dead end, and therefore planning is necessary. The size of the full graph grows exponentially with the size of the problem. If a problem is more complicated in our toy example, the size of the graph often contains millions of nodes. Searching all of these nodes to find a solution is very ineffective and unlikely what humans are doing. We want a way to not have to search the entirety of the graph, to break it down into parts. So we could introduce a state as a subgoal like we did earlier, but how would we choose a state given that there are millions of them? The classical approach in hierarchical planning is to try to bound the search graph directly, thereby limiting search depth. However, instead of changing the state action graph, we can instead make use of the visual nature of the task and change the visual input to the planner instead. This is the same fundamental operation as folding a map. Choosing a regular area to focus on also narrows the search tree. Even though our operation here is regular, the effect on the search tree is less than regular, and this is the big intuition behind this project, that simple changes to the visual input to a system can have complex effects on the abstract graph used for planning behavior. In this project, I'm investigating one particular method of augmenting the visual environment to shape the action planning graph. That method is visual scoping. So let's look only at the left-hand side of the tree. It's big enough as it is. How does planning and the visual scoping work? Here, we use horizontal slices of the target structure. We know from prior work that people tend to construct buildings layer by layer. And we focus only on what is inside the selected area, the scope, when planning and ignore the rest for now. Like a subgoal, this cuts down on the size of the graph that we need to search. After we have found a solution to a subgoal, and do note the new green and red states, we take the actions and choose the next subgoal using visual scoping. And because the actions have been committed, the search starts again from a new starting point. Here, the scope always moves upwards and changes only in size, when it can have a narrow or tall scope. However, the strategy is not guaranteed to succeed. Visual scoping might go wrong too. If you first select the scope, build it, we have backed ourselves into a corner. There's no way to build this remaining part because there's no one-by-one piece. Therefore, we need to be clever about how we select the scope. So, how are we selecting how much to bite off in the next subgoal? Do we choose a small subgoal that is going to be easy to plan, or do we choose a large one that allows us to make faster progress towards the full structure? Under the model, this is how the next subgoal is chosen. We balance the progress, what percentage of the target can I solve with this subgoal, with the planning cost of finding a solution to the subgoal. The action planning cost is how many states in the graph do we need to search across to find a solution. How do we trade off between progress and cost? By changing how costly action planning is to the planner. Sometimes it's easier for the planner to invest more time into actual planning depending on context. If it's expensive, slow for the planner to search the graph, then we prefer easy to solve subgoals. If planning is cheap, then we can choose a few subgoals and reduce the time needed to select subgoals. This way, we can express cognitive resource limitations. To study the effect of visual scoping on planning behavior, we need to situate it in the larger space of planning strategies. Consider the space of planning strategies between those that spend a lot of upfront work to make searching the graph easier and those that spend no upfront work. One baseline is not using visual scoping at all, but to instead search the entire graph directly. That is the no visual scoping planner, the naive approach. On the other end of the spectrum, we have exhaustive visual scoping. Here, we start with a target, then we identify all sequences of visual scopes to find the cheapest sequence of subgoals. Only after the planner has broken down the entire problem into subgoals do we start to build. This is the traditional way of doing subgoal decomposition and notoriously a very hard task for artificial intelligence systems to solve. And in the middle sits an interactive strategy. What if we only chose how much of the problem to focus on next, not caring about the rest for now? Under incremental visual scoping, we identify only the next visual scope at a time, build it, and then choose the next one. So we interleave planning and acting, deciding at every turn how much of the problem we attack now versus keeping it for later. The next subgoal is selected according to how costly action planning is to the planner. So this is clearly requiring less computation to find subgoals compared to exhaustive visual scoping. This comes at a cost, and we'll talk about that later, but the hope is that this is a beneficial trade-off, that we wouldn't lose much accuracy while reducing the total cost of planning. So, we know that exhaustive visual scoping is going to find a sequence of subgoals that makes planning easiest because it considers all of them. No visual scoping planning will have no visual scoping cost, but the highest action level cost. How can incremental visual scoping balance these two costs? To investigate these questions, we ran a series of simulations using these models in the block construction task. First, how does visual scoping change the action planning cost and success of planning? In other words, what is the speed accuracy trade-off of these three planners? Here, the x-axis means success, the rate at which target structures can be perfectly reconstructed by the planner. On the y-axis, you see average action planning cost, and this is measured in how many nodes of the graph did the planner search over before it found a solution. First, let's look at no visual scoping. This strategy only finds the solution 40% of the time before either making a mistake or timing out. The search had a large, but not an infinite computational budget. Scoping achieves twice as many perfect reconstructions, and the solutions it finds are much cheaper as well. Finally, exhaustive visual scoping can solve the problem every time and at a low cost. This was to be expected as it finds the cheapest sequence of subgoals in advance. So, the use of visual scoping generally indeed reduces the cost of searching for actions and increases the success of the planner. This reproduces prior work on the usefulness of subgoals. However, what about the cost of choosing these subgoals by performing visual scoping in the first place? On the right, the cost of performing visual scoping is shown on the y-axis. Here, we measure it as the cost of determining the action planning cost of each potential subgoal, and we do that by actually searching the actions for each potential subgoal. And while this is clearly not a plausible proposal for how people might do this, the cost of choosing subgoals using some other evaluation metrics for potential subgoals arguably scales with the number and size of potential subgoals. Therefore, the general pattern should hold even when using a different method to estimate the cost of all potential subgoals, even though the magnitude of visual scoping cost will be different. The x-axis here shows the same rate of success as on the left. Action level doesn't have a visual scoping cost, of course, and this is incremental scoping. And finally, the cost of selecting visual scopes using exhaustive visual scoping is larger by an order of magnitude compared to incremental. Therefore, while exhaustive visual scoping has a lower action planning cost, it is much more expensive compared to incremental when it comes to choosing those subgoals. So, the incremental planner trades a decrease in success rate against a huge decrease in visual scoping cost. There are different ways to search the graph, and would have shown you other results using breadth first search look ahead, a classical search algorithm. To show that the effect of scoping is robust across different search algorithms, we've trained the same models using different graph search algorithms. Here, you see the same plots with A-star look ahead included. Same general pattern holds, indicating that the effect of visual scoping is robust and does not depend on particularities of the search algorithm. As I mentioned earlier, the visual scoping planner balances how much to plan now versus later, depending on the costliness of action planning, how much you value running costs over making progress. Let's try to better understand this trade-off based on the costliness of planning. On the y-axis, you see action planning costs and states evaluated like before. On the x-axis, you see the parameter governing the costliness of action planning, where 0 means the planner only cares about making progress, and higher value mean that it really wants to avoid costs. As expected, the costlier action planning is, the lower the total cost of searching for actions given a subgoal. This means that the trade-off is working as intended. Note that the no visual and exhaustive visual scoping planners both do not make this trade-off. The former because it doesn't use subgoals, and the latter because it always chooses the optimal sequence of subgoals anyway. That's why they're flat. So, the more difficult action planning is to the planner, the less of it has to do by choosing easy to solve subgoals. Does this come with unintended consequences? Namely the cost of visual scoping. Same plot as before, just with visual scoping on the y-axis. Other two planners are off screen. The visual scoping cost increases the cost the action planning is, and that might seem paradoxical, but it is because if we choose smaller subgoals, then we need more of them, therefore the total cost of choosing them is higher. And this illustrates how momentary cognitive resource limitation can lead to a higher total amount being used. You're trying to be stingy, but you end up paying a larger cost choosing subgoals that minimize action planning cost. Finally, what does this trade-off mean for the rate of success? Does choosing easier to solve subgoals make one more myopic, more prone to getting stuck in dead ends? And y-axis here is rate of success. Indeed, the higher the costliness of action planning, the more mistakes the planner makes. Easier to solve subgoals are more likely to lead it into a dead end. But look at the left-hand side, where the costliness is low, but not 0. Here, the incremental visual scoping planner achieves a 100% success rate, the same as the exhaustive planner, but still a fraction of the visual scoping cost. That means that on the task presented here, incremental scoping can achieve the success of the much more expensive exhaustive planner. So, incremental visual scoping explains trading of easier action planning against more subgoal searching and a lower success rate, where the sweet spot depends on the preferences of the planner, but the point being, you don't get anything for free. To summarize the model results, having subgoals for visual scoping indeed makes action planning easier. Incremental visual scoping can approximate the success of exhaustive visual scoping, but at a much smaller cost of searching subgoals. So, we have a model that can solve these kinds of physical assembly tasks using these different strategies. Now we can ask, which of these strategies best explains human behavior on the same task? So in these future experiments, we can make use of the fact that we can give the same block tower reconstruction task that we gave to the models to people. And here we can use visual scoping in two ways. First, we can use it to induce subgoals to investigate human action planning conditional on a certain sequence of subgoals. But we can also use it to study the choice of subgoals itself. Unlike the actions that people take, which subgoals they use is usually invisible. However, under visual scoping, we can make use of the visual nature by making participants mark out their next subgoal on the target shape itself, and this way the choice of subgoal becomes measurable. Again, these are future experiments, but they illustrate how visual scoping might be used to manipulate and observe subgoal planning behavior. So, what I've discussed is specific to the block tower reconstruction task and the specific decisions made when studying visual scoping. But I want to zoom out a bit. Manipulating what we see to help in planning is pervasive in human decision making beyond solving these puzzles. Say you're planning a talk. You might have a couple of PDFs open in Windows arranged on the screen, you'll have some browser tabs that you arrange in a certain order, and maybe a statistics notebook. Understanding how we arrange the visual information around us might shine light on a wide variety of planning tasks.